Unless there are any reported issues after the close of the election, independent election key holders convene. Each has a key they made for themselves and the key that they gave us to make the blank ballots. Only by coming together can they process the receipts back into votes we can count. These are the secret positions which each give the correct location of the candidate names. When we go get these for all receipts, then we shuffle the batch so the votes we decrypt can't be linked back to the receipts. If you voted first on this system, we don't want your vote to be decrypted first, or this would put your privacy at risk. We are going to illustrate the vote this time as a preference order rather than a simple S. This way you can see how the whole ballot is protected, not just the single mark the voter makes. So let's say the voter provided a preference order vote with 4 choices in order. We will reorder these blue numbers to the voter's preference order, and we are done with the receipt. This is all we need to get back the voted list. Now we recover the legal order of the shuffled list. We showed how math is the key to this, but in the following examples, we are using only very small numbers. In a real election, these numbers are 100 digits long. Each of the key holders performs their part of the decryption. They do it like this. We take the first secret position. Our key holder uses their private key, which is just the number they know. We take the public key, which did the encryption. The first key holder does this. We need at least 3 key holders. The other 2 key holders do the same with their keys. So we have 3 values, 41, 16, and 21. Now we combine them. That's our combined decryption. Now we get the secret and use it. So this is candidate number 2, which is Jamie. He gets the voter's third preference. The key holders repeat the math the same way to get the rest of the ballot, which is 2, 1, 4, 3. And there's the vote we can count. This is done for all the receipts. They are hand counted or the vote data are machine counted. But how does Jamie know the key holders did the right thing with each math operation? Each key holder has to emit a proof at each step. Since decryption is just math, we can actually provide some of the details of the steps they used just to show it was done right, but without giving away the private keys the key holders have. Why don't we just hand over the private keys so you and I can do our own decrypt? The answer is that decrypt must happen under conditions where the keys cannot be used to align any one receipt with its vote. If anyone had the keys after the election, they could go back and work out what your vote was from your receipt. So instead, we are going to make the key holders give us some of their workings, just enough to show they did the right thing.